In the pre-dawn stillness of November 4th, 1943, at 5 a.m., a profound shift occurred within Bethel Valley near Oak Ridge, Tennessee. Behind layers of barbed wire, across treacherous mud roads, shrouded in an impenetrable veil of military secrecy, a monumental machine crossed an invisible threshold. The X-10 Graphite Reactor, with a silent, profound hum, went critical. This was not the first time a nuclear reactor had achieved such a feat. That singular distinction belonged to Chicago Pile 1 nearly a year earlier, in December of 1942. Yet, X-10 represented something entirely new, something far more ambitious. It was conceived not as a fleeting experiment, a momentary flash of scientific triumph. Instead, it was engineered as a relentless workhorse, a crucible designed to run continuously, to instruct, and to unequivocally prove that the theoretical possibility of plutonium production could be forged into an industrial reality. Here lay the profound contradiction. The very reactor that would unlock the plutonium pathway, paving the way for a new era of warfare, was not the gargantuan production facility that would eventually feed the burgeoning bomb program. X-10 was smaller, a temporary structure, cooled by air, a mere pilot plant. Still, this unassuming in-between machine might well have been one of the most critical engineering bridges in the entire Manhattan Project. X-10 was never built to capture headlines. Its purpose was far more urgent, far more demanding, born from the crucible of wartime necessity. It was built to answer a singular, agonizing question. Could the United States transform plutonium from a mere laboratory curiosity into a repeatable, scalable production system before the sands of time ran out? This undertaking demanded infinitely more than simply making a reactor function. It necessitated the construction of an entire, seamless chain of processes, each link fraught with unprecedented challenges. Raw uranium had to be meticulously prepared and fed into the core. Neutrons, the invisible architects of transformation, had to perform their intricate dance. Irradiated fuel, now lethally radioactive, had to be safely extracted. This intensely hot material then required a period of controlled cooling, a dangerous waiting game. Chemists, working in conditions that defied imagination, then faced the daunting task of dissolving the fuel, separating minute quantities of plutonium from a fiercely radioactive, corrosive mess. Finally, the precious, newly isolated plutonium had to be delivered to the scientists laboring to design a weapon of unimaginable power. All of these intricate, perilous steps had to be mastered, refined, and made repeatable before the colossal, full-scale plants at Hanford were even ready to begin their work. This, then, is not merely the chronicle of a reactor. It is the story of the machine that fundamentally taught America how plutonium production truly functioned in the unforgiving crucible of the real world. And once one grasps the profound significance of X-10, a larger truth emerges, stark and undeniable. The Manhattan Project was not solely a triumph of physics, a theoretical breakthrough. It was, at its very core, a pilot plant breakthrough, a testament to industrial innovation on an unprecedented scale. To fully comprehend the immense weight X-10 carried, one must rewind to the closing days of 1942. On December 2nd of that year, Enrico Fermi and his brilliant team had achieved the impossible. The first self-sustaining, controlled nuclear chain reaction within Chicago Pile 1, nestled beneath the stands of Stagg Field at the University of Chicago. That moment, a quiet flicker of genius, definitively proved that a graphite-moderated reactor could indeed work. But proof of principle, however groundbreaking, was insufficient for the brutal demands of global war. The conflict did not call for a scientific demonstration. It demanded a clear, viable, and industrial-scale production path. By then, American strategists understood there were two primary routes toward an atomic weapon. One relied on uranium-235, an isotope so rare it had to be painstakingly physically separated from its far more common sibling, uranium-238. The other path, the one X-10 was destined to illuminate, involved the creation of an entirely new element, plutonium. The fate of nations hinged on which of these paths could be industrialized first. In the pre-dawn stillness of November 4th, 1943, at 5 a.m., a profound shift occurred within Bethel Valley, near Oak Ridge, Tennessee. Behind layers of barbed wire, across treacherous mud roads, shrouded in an impenetrable veil of military secrecy, a monumental machine crossed an invisible threshold. The X-10 Graphite Reactor, with a silent, profound hum, went critical. This was not the first time a nuclear reactor had achieved such a feat. That singular distinction belonged to Chicago Pile 1, nearly a year earlier, in December of 1942. Yet X-10 represented something entirely new, something far more ambitious. It was conceived not as a fleeting experiment, a momentary flash of scientific triumph. Instead, it was engineered as a relentless workhorse, a crucible designed to run continuously, to instruct, and to unequivocally prove that the theoretical possibility of plutonium production could be forged into an industrial reality. Here lay the profound contradiction. The very reactor that would unlock the plutonium pathway, paving the way for a new era of warfare, was not the gargantuan production facility that would eventually feed the burgeoning bomb program. X-10 was smaller, a temporary structure, cooled by air, a mere pilot plant. Still, this unassuming in-between machine might well have been one of the most critical engineering bridges in the entire Manhattan Project. X-10 was never built to capture headlines. Its purpose was far more urgent, far more demanding, born from the crucible of wartime necessity. It was built to answer a singular, agonizing question. Could the United States transform plutonium from a mere laboratory curiosity into a repeatable, scalable production system before the sands of time ran out? This undertaking demanded infinitely more than simply making a reactor function. It necessitated the construction of an entire, seamless chain of processes, each link fraught with unprecedented challenges. Raw uranium had to be meticulously prepared and fed into the core. Neutrons, the invisible architects of transformation, had to perform their intricate dance. Irradiated fuel, now lethally radioactive, had to be safely extracted. This intensely hot material then required a period of controlled cooling, a dangerous waiting game. Chemists, working in conditions that defied imagination, then faced the daunting task of dissolving the fuel, separating minute quantities of plutonium from a fiercely radioactive, corrosive mess. Finally, the precious, newly isolated plutonium had to be delivered to the scientists laboring to design a weapon of unimaginable power. All of these intricate, perilous steps had to be mastered, refined, and made repeatable before the colossal, full-scale plants at Hanford were even ready to begin their work. This, then, is not merely the chronicle of a reactor. It is the story of the machine that fundamentally taught America how plutonium production truly functioned in the unforgiving crucible of the real world. And once one grasps the profound significance of X-10, a larger truth emerges, stark and undeniable. The Manhattan Project was not solely a triumph of physics, a theoretical breakthrough. It was, at its very core, a pilot plant breakthrough, a testament to industrial innovation on an unprecedented scale. To fully comprehend the immense weight X-10 carried, one must rewind to the closing days of 1942. On December 2nd of that year, Enrico Fermi and his brilliant team had achieved the impossible. The first self-sustaining, controlled nuclear chain reaction within Chicago Pile 1, nestled beneath the stands of Stagg Field at the University of Chicago. That moment, a quiet flicker of genius definitively proved that a graphite-moderated reactor could indeed work. But proof of principle, however groundbreaking, was insufficient for the brutal demands of global war. The conflict did not call for a scientific demonstration. It demanded a clear, viable, and industrial-scale production path. By then, American strategists understood there were two primary routes toward an atomic weapon. One relied on uranium-235, an isotope so rare it had to be painstakingly physically separated from its far more common sibling, uranium-238. The other path, the one X-10 was destined to illuminate, involved the creation of an entirely new element, plutonium. The fate of nations hinged on which of these paths could be industrialized first. The other, a truly artificial element, was based on plutonium-239. Its genesis was a complex ballet of atomic forces. Uranium-238, an abundant but inert isotope, would absorb stray neutrons within the heart of a reactor, then undergo a swift, cascading sequence of radioactive transformations. On paper, this pathway to a new, potent material shimmered with the promise of unprecedented power. But the moment a concept gleams on the blueprint, the relentless crucible of engineering begins its interrogation, posing questions both precise and profoundly unforgiving. Could a reactor sustain its chain reaction not for mere fleeting moments, but continuously, day after day, week after week? Could this colossal undertaking rely on natural uranium, a readily available resource, given that the enrichment of uranium-235 remained a monumental, agonizingly slow process? How would the colossal, destructive heat generated by such a process be tamed, channeled, prevented from consuming the very machinery designed to create its product? Could the fuel, highly radioactive and deadly, be inserted and removed with the surgical precision of a factory line, on a schedule dictated by the demands of war? And the chemists, the unsung alchemists of this new age, could they extract the minute quantities of plutonium from the intensely irradiated uranium slugs without sacrificing their own lives to the invisible, insidious enemy of radiation? Crucially, could this entire, fragile, dangerous system be scaled, transformed from a laboratory marvel into an industrial behemoth, vast enough to fuel a wartime bomb program that would redefine global power? It was into this maelstrom of theoretical possibility and staggering practical charward. Alongside him stood Arthur Compton, a Nobel laureate wrestling with the fundamental physics, and Enrico Fermi, the quiet genius who had already coaxed the first self-sustaining nuclear chain reaction into existence. They were joined by the industrial might of DuPont, the intellectual powerhouse of the metallurgical laboratory, and the rapidly burgeoning, intensely secretive reservation carved out of the Tennessee landscape, Oak Ridge, then known only by its bureaucratic designation, the Clinton Engineer Works. Oak Ridge is often etched into history for its relentless pursuit of uranium enrichment, a reputation justly earned. Yet, in the pivotal year of 1943, it simultaneously became the proving ground for the plutonium pathway, a parallel quest of equal, if not greater, complexity. The reactor constructed there, variously known as X-10, the Clinton pile, or simply the graphite reactor, was never conceived as the ultimate, full-scale production machine. Its purpose was far more nuanced, more strategically vital. It was a semi-works facility, what engineers with their pragmatic lexicon would term a pilot plant. It was designed to be large enough to unveil the brutally real operational problems inherent in a full-scale system, yet small enough to be constructed with a speed that defied the very laws of conventional engineering. This distinction was everything. The Chicago Pile 1 had unequivocally demonstrated the foundational physics, proving that a self-sustaining chain reaction was not a theoretical fantasy, but a tangible reality. Hanford, a sprawling, remote expanse in Washington state, was earmarked to become the industrial heartland, the site of mass production. But X-10, nestled in the rolling hills of Tennessee, was the indispensable bridge connecting these two worlds. It was here that the audacious gamble would be tested. Could the reactor itself, the intricate machinery for handling its deadly fuel, and the perilous chemical processes for extraction all function as one cohesive working system, a factory of the future built on the very edge of the unknown? What they could not fully grasp at the outset was that the most formidable hurdle would not merely be coaxing a reactor to achieve criticality and sustain it. The true, agonizing challenge would be to force an entire, unprecedented plutonium workflow, from raw uranium ore to purified fissile material, to behave with the predictable, relentless efficiency of a factory. The X-10 problem, therefore, was not a singular obstacle, but a formidable stack of interconnected, mutually dependent challenges. First among these was the very core of the reactor itself. The machine had to operate exclusively on natural uranium. The colossal, energy-intensive process of large-scale uranium enrichment remained unfinished, a bottleneck in the war effort. This mandate meant that the neutron economy within the reactor had to be nothing short of exquisite. Every precious neutron, unleashed by fission, had to be carefully managed, its journey meticulously controlled. The reactor demanded a moderator, a substance capable of slowing down these high-energy neutrons without greedily absorbing too many of them. A delicate balance essential for sustaining the chain reaction. In the American program, this critical role fell to graphite. But not just any graphite. It had to be graphite of an unheard-of purity, meticulously refined to purge every trace of impurities that could act as neutron poisons, threatening fatal losses that would extinguish the nascent chain reaction before it could ever truly ignite. Second, and perhaps most immediately terrifying, was the issue of heat. Any reactor designed to transmute uranium into plutonium necessarily generates an immense, almost unimaginable quantity of heat. This was not merely a byproduct, it was a direct consequence of the furious atomic dance occurring within the core, a visible manifestation of the raw energy being unleashed. The very heart of a nuclear reaction generates a searing, unimaginable heat. This thermal energy, a byproduct of atomic fission, demanded a solution for its safe and reliable removal. Without it, the entire endeavor would simply melt into catastrophic failure. For the X-10 reactor, the relentless pace of wartime dictated every decision. Speed was paramount. DuPont, entrusted with the monumental task, opted for air cooling. It was a simpler system, faster to construct within the confines of a pilot plant. Massive fans, roaring with tireless effort, would draw vast volumes of air through the reactor's intricate channels, carrying away the lethal heat. This approach served its immediate purpose, a practical choice for a proof-of-concept facility. Yet even as X-10 rose from the Earth, DuPont's engineers had already concluded that the gargantuan reactors envisioned for Hanford, designed for unprecedented scale, would demand a far more robust system. Water cooling. Air could ignite a pilot. Water promised the sustained power of industrial-scale production. Beyond the immediate engineering hurdles, a third, often overlooked challenge loomed: chemical separation. A nuclear reactor, at the end of its cycle, does not simply yield pure, gleaming plutonium. Instead, it produces irradiated uranium fuel, a deadly cocktail teeming with fission products, radiating extreme radioactivity, and containing only microscopic quantities of newly formed plutonium buried deep within its structure. The Manhattan Project urgently required a method to chemically extract this precious plutonium from material too dangerous for any direct human contact. The leading contender was the bismuth phosphate process. Conceptually brilliant, its practicality remained unproven under the most harrowing conditions. It demanded validation using actual irradiated fuel sourced from a functioning reactor, with operators working remotely, shielded by formidable barriers of concrete and lead. This meant the X-10 facility bore a dual burden of proof. First, it had to demonstrate beyond any doubt that plutonium could be reliably created within a reactor's core. Second, it had to establish that this elusive element could then be successfully separated from the intensely radioactive fuel in a repeatable industrial-scale process. This profound dual mandate shaped every aspect of the plant's physical design. At its core stood a monolithic cube of graphite, measuring 24 feet on each side, encased in an impenetrable shell of thick, high-density concrete shielding. The front face of this colossal structure was perforated by 1,248 horizontal channels, each a conduit to the reactor's heart. Into these channels, workers meticulously loaded slugs of uranium metal, using long, precisely engineered rods, maintaining a critical distance from the deadly material. Cooling air surged through these channels, circulating around the uranium slugs, carrying away their nascent heat. After the prescribed period of irradiation, a new sequence of operations would begin. Fresh slugs were carefully pushed in from the front, displacing the now intensely radioactive ones. These spent slugs then dropped from the back of the reactor into a specially designed chute, plunging into a deep, water-filled container. The water provided an immediate, vital layer of shielding and cooling, containing the lethal energy within its depths. It sounds almost mechanical, almost a matter of routine, but the reality was anything but. Every single stage of this intricate dance involved a terrifying calculus of radiation exposure, precise timing, critical geometry, constant cooling, rigorous contamination control, and an unwavering discipline from every operator. The very material they sought, the useful product, became exponentially more dangerous the instant it was created. The hotter the fuel, the more challenging it became to touch, to move, to store, and to process. Thus, X-10 was far more than just a reactor. It was designed to function as a complete, full-scale production rehearsal, a proving ground where the theoretical met the terrifying practical, forging the blueprint for an entirely new and profoundly dangerous industrial age. Yet, even with its successful construction and the achievement of criticality, an even larger, more existential fear still cast its long shadow over the entire project. A question that transcended engineering and chemistry, touching the very fabric of human existence. The air hung heavy with a question that could decide the fate of nations. Would a preliminary pilot plant, a scaled-down experiment, ultimately preserve precious time by averting unforeseen catastrophe? Or would it merely consume resources and delay a project that could not afford a single wasted moment? This was no idle academic debate. It was a profound dilemma at the heart of the most ambitious and desperate undertaking in human history. The answer, etched into the very foundations of industrial ingenuity, was clear, ancient, and deceptively simple. Construct the pilot before staking everything on the full-scale gamble. This foundational engineering principle, tested across centuries of human endeavor, became the bedrock upon which the unprecedented challenge of atomic power would rise or fall. It was this unwavering conviction that elevated the X-10 reactor, nestled deep within the clandestine world of Oak Ridge, far beyond a mere nuclear device. It was conceived as a comprehensive systems test, a living laboratory designed to validate an entire, unimaginable industrial chain. Construction unfurled with a speed that defied all conventional logic. In the span of roughly 10 months, a period barely long enough to draft initial blueprints in peacetime, the X-10 facility was not only designed but brought to life. A first-of-its-kind nuclear reactor, interwoven with its intricate, highly specialized chemical processing facilities, would, under any other circumstances, have demanded years, perhaps even a decade, of meticulous planning and construction. But the world was engulfed in the inferno of global war, and the relentless ticking of the clock dictated every decision. The pressure on Oak Ridge was immense, a constant, crushing weight. Across a landscape once defined by rolling hills and quiet forests, a new, secret city erupted from the earth. Roads were carved, utilities laid, housing blocks assembled, and laboratories, support structures, and highly complex technical installations all manifested simultaneously. Oak Ridge itself was a work in progress, a sprawling, clandestine metropolis still taking shape even as the X-10 reactor within its heart began to coalesce into a tangible reality. At the core of this burgeoning scientific fortress, inside the reactor's shielded mass, the design logic was elegantly straightforward, yet its execution demanded absolute precision. Graphite blocks, meticulously arranged, served as the silent architects of nuclear transformation, slowing the frenetic neutrons unleashed by atomic fission. Into this controlled environment, uranium slugs, specially prepared, were introduced, acting as both fuel and alchemical reagents. A fraction of the uranium-238 nuclei, after capturing these slowed neutrons, underwent a profound metamorphosis through radioactive decay, transmuting into the elusive and deadly plutonium-239. Control rods, precisely manipulated, served as the ultimate arbiters of this invisible fury, regulating the chain reaction with an iron grip. A constant torrent of air, forced through the reactor's core, acted as a vital coolant, tirelessly battling the intense heat generated, preventing a runaway thermal cascade. Fuel entered from one side, a steady procession of raw potential, and after its incandescent journey, emerged from the other, utterly transformed. This was merely the reactor's intricate ballet. Then came the equally demanding and perhaps even more dangerous chemical half of the process. Once irradiated, the uranium fuel slugs were no longer inert objects. They had become profoundly altered entities, saturated with a deadly cocktail of new, highly radioactive elements, including the precious, perilous plutonium. Before any further handling, they required a period of intense, controlled cooling, submerged within vast tanks of shielded water, allowing their most violent radioactivity to subside. Only then could they be gingerly transferred into the adjacent separation plant, a fortress of concrete where human operators worked not directly but remotely, their hands guided by unseen mechanisms, shielded by walls thick enough to absorb lethal radiation. Within these heavily fortified chambers, the bismuth phosphate process reigned supreme. In essence, a team of brilliant, determined chemists exploited plutonium's unique property of changing its oxidation states. This allowed them to guide the element through a series of precipitation steps, carefully coaxing it to solidify and separate from the vast majority of the uranium and the myriad of other highly radioactive fission products that contaminated the spent fuel. It was a process utterly devoid of modern elegance. It was repetitive, arduous, and inherently dirty, demanding constant, heavy shielding for every step. Yet, it possessed one singular, overwhelming virtue, a characteristic that overshadowed all its imperfections. It could be scaled up. And in the desperate crucible of wartime, scalability was the only metric that truly mattered. The massive production facilities planned for Hanford did not require a chemically beautiful or aesthetically pleasing process. They demanded a system that worked flawlessly and repeatedly under the most rigorous industrial production conditions imaginable. The true, epoch-making breakthrough arrived when the X-10 facility unequivocally demonstrated that the reactor and its intricate separation plant could function not as two disparate entities, but as a single, cohesive, operational chain. Fuel could be irradiated with precision, then safely removed, meticulously stored, carefully dissolved, chemically processed, painstakingly purified, and finally, accurately measured. This seamless, unprecedented flow transformed plutonium from a theoretical concept, a mere product of abstract physics, into a tangible industrial substance, a deadly reality forged in the heart of a nuclear furnace. But X-10 achieved something else, an accomplishment equally profound, equally vital, and perhaps even more enduring. It validated the very premise of its existence. It proved, beyond any shadow of doubt, that the time, the resources, the sheer human effort poured into its construction were not wasted. Instead, they were an investment, a shield against catastrophic failure, a testament to the wisdom of building a pilot before gambling on the full-scale dream. It was the ultimate vindication of foresight, a blueprint for the future, ensuring that the grand, dangerous vision could indeed be brought to life, not just theoretically, but practically, reliably, and with a terrifying, unprecedented efficiency. Across the sprawling, secretive landscape of a nation hurtling towards a new age, a singular facility became the crucible for an entire generation of scientific and technical pioneers. Engineers, operators, chemists, safety officers, and maintenance specialists all converged on this site, their hands-on experience forged in the intense heat of necessity. Before the monumental production operations at Hanford could even conceive of taking shape, this place, known only as X-10, was already at work. It was not merely teaching a system, it was shaping the very workforce destined to command it. To label X-10 a pilot plant is not to diminish its monumental significance. It is, in fact, to underscore its profound purpose. A pilot plant is the unforgiving arena where elegant theories, meticulously crafted on blackboards and in blueprints, are brutally forced to confront the unyielding realities of the physical world. Here, the abstract met the tangible, the stubborn resistance of valves, the relentless demands of schedules, the delicate yet dangerous dance of remote manipulators, the insidious threat of contaminated equipment, the soul-crushing burden of maintenance headaches, and the ever-present, inescapable specter of human error. This was precisely the crucible X-10 offered to the nascent plutonium program. Yet this was only the prelude. The most critical, the most terrifying proof still lay ahead. The moment when an intricate design, a theoretical construct, would have to cease being an idea and begin its existence as a living, working reactor. That moment arrived with the pre-dawn chill of November 4th, 1943. At precisely 5 o'clock in the morning, the X-10 Graphite Reactor achieved criticality. In the precise lexicon of nuclear engineering, this did not signify a cataclysmic explosion or some dramatic, uncontrolled burst of energy. Instead, it marked a profound, controlled transformation. The neutron chain reaction, a cascade of subatomic events, had become entirely self-sustaining at a meticulously managed level. The machine, once dormant, was now undeniably alive in the only sense that truly mattered. With this vital threshold crossed, the true work began. The reactor pile's power level, a measure of its internal energy, was increased with painstaking deliberation, step by careful step. Fuel rods, packed with uranium, were subjected to the relentless bombardment of neutrons, initiating the alchemical process of transmutation. In laboratories adjacent to the reactor, chemists, who had until now only handled theoretical samples and simulated compounds, began the perilous task of processing genuine reactor products. These were not mere academic curiosities. They were the very substances that would define the future. By the close of November 1943, less than a month after its first breath, X-10 had already delivered undeniable proof of its capability. It could produce plutonium. This revelation resonated with immediate and profound consequence. The pilot plant, having proven its mettle, began to dispatch purified plutonium samples. each atom a testament to the new era. One of the earliest, most meticulously guarded shipments involved a mere 1/5400th milligrams of purified plutonium, carefully transported from Oak Ridge to the University of Chicago. This minuscule quantity, barely visible to the naked eye, carried the weight of a world on its shoulders. As the program accelerated, X-Ten's role expanded dramatically. It became the primary supplier to Los Alamos, providing the first truly significant quantities of plutonium essential for the intricate fission studies and groundbreaking weapon design research. This distinction between destinations and purposes was not merely administrative, it was fundamental. Chicago received early, highly purified material destined for fundamental scientific inquiry. Los Alamos, in stark contrast, received larger research quantities, precisely calibrated to help the bomb designers comprehend plutonium not as an abstract element, but as a tangible, terrifying weapon material. And those studies, conducted in the desert laboratories, fundamentally altered everything. Initially, a flicker of hope existed that plutonium might function within a relatively straightforward gun-type weapon, conceptually similar to the design envisioned for the uranium bomb. But the plutonium bred within the M position, a subtle variation in its atomic structure, made the premature initiation of a chain reaction far more probable than weapon designers could ever tolerate. The terrifying prospect of a fizzle, a weapon that failed to achieve its full, devastating potential, loomed large. This unforeseen reality violently wrenched the entire design effort away from simplicity and forced it onto the infinitely more challenging path of the implosion approach. X-10, then, was doing far more than simply manufacturing plutonium. It was revealing the very nature of this new element, exposing its inherent complexities, and in doing so, it was dictating the future trajectory of the most destructive force humanity had ever conceived. It was not just a factory, it was a truth-teller, a silent, powerful arbiter of destiny, forcing the world to confront the profound, often unwelcome realities of the atomic age it had helped to birth. It was a silent, relentless pursuit, quietly defining the very nature of a weapon that would forever alter the course of human history. This was the work of the X-10 reactor, its purpose etched into every atom it split. Simultaneously, a dedicated chemical separation plant achieved a breakthrough of monumental proportions. It validated the bismuth phosphate process, a method that would later become the indispensable backbone of the full-scale separation facilities at Hanford. This validation, often overlooked, stands as perhaps the most profoundly underrated achievement in the entire narrative. Bombs, in their terrifying finality, are not born from isolated research alone. They emerge from a complex, intricate dance between raw scientific theory and the gritty reality of industrial engineering. Reactors, when coupled with successfully scaled chemical processes, are the crucible where inert materials transform into the fissile substances that can actually be studied, understood, and ultimately weaponized. By 1944, the X-10 reactor's operational power had been pushed far beyond its initial design parameters. The system, a testament to wartime urgency and ingenuity, was performing precisely as a pilot plant should. It was generating product, yes, but more critically, it was unmasking the myriad operational issues that only real-world application can reveal. It was a rigorous, unforgiving teacher, instructing engineers on what elements of its design the larger system needed to meticulously replicate, and, perhaps even more importantly, what demanded radical alteration. Among the clearest, most impactful lessons learned was the critical importance of cooling. The X-10's air cooling system had been a pragmatic choice, perfectly suited for a facility constructed with astonishing speed under immense pressure. Yet its very success illuminated the inherent limitations of that choice. The colossal Hanford reactors, designed for a scale of production previously unimaginable, would move forward with water cooling. This decision was not arbitrary. It was a direct reflection of the exponentially greater heat loads and the staggering production expectations that defined the Hanford mission. This dynamic of rapid iteration, of learning and adapting under fire, is the quintessential hallmark of wartime engineering. The X-10 did not achieve its profound success by being flawlessly copied. Its true triumph lay in its capacity to illuminate, with stark clarity, precisely what should and should not be replicated. And so, by the close of 1943, Oak Ridge had solidified its position as the indispensable plutonium pilot. As 1945 dawned, the X-10's central wartime role in plutonium pilot production began its inevitable fade. The full-scale industrial complex at Hanford had assumed the mantle of the primary mission, taking over the demanding task of large-scale production. But by then, the X-10 had already fulfilled, with breathtaking efficiency, the monumental purpose for which it was conceived. It had unequivocally proven that a graphite-moderated reactor could operate continuously, reliably, and practically within a production setting. It had established and refined the intricate procedures for fuel loading and discharge, navigating the perilous complexities of real radiological conditions. It had demonstrated, beyond any doubt, the feasibility of remotely processing irradiated uranium within the shielded confines of a chemical plant. Furthermore, it had served as a vital training ground, forging the expertise of countless individuals who would go on to staff the far larger plutonium operations. But its most profound contribution, the one that resonated with the highest stakes, was the production of the critical plutonium samples. These minute, meticulously prepared samples were not just byproducts, they were the very keys that unlocked the secrets of this new, terrifying element, allowing scientists to understand the material around which they were designing the ultimate weapon. This stands as an extraordinary record for a machine constructed with such haste, under the crushing weight of wartime pressure and unprecedented scientific uncertainty. And then, the X-10 accomplished something equally remarkable, something that spoke to its enduring legacy far beyond the conflict it was built to serve. It survived its original mission. After the war concluded, the reactor underwent a profound metamorphosis, shifting its focus from weapon production to the noble pursuit of research and radioisotope generation. It became an essential cornerstone, part of the very foundation upon which the Oak Ridge National Laboratory would evolve and flourish. The X-10, originally conceived for destruction, helped to usher in the peacetime era of nuclear science, facilitating the distribution of life-saving isotopes and pioneering the very first systematic studies of reactor dynamics. Its journey from the crucible of war to the vanguard of scientific exploration encapsulates the profound, often unexpected, trajectory of human ingenuity. For years, the graphite reactor at Oak Ridge served a purpose far removed from the cataclysmic forces it was designed to harness. It became a crucible for radiation health investigations, a fertile ground for pioneering materials research, and a quiet engine driving the nascent fields of nuclear medicine. Its second life, a period of sustained scientific inquiry, cemented its legacy in ways its wartime architects could scarcely have imagined. Then, in 1948, a singular event etched the reactor into the annals of history, a moment of profound symbolism that resonated across a world yearning for peace. The X-10 reactor, a machine born of wartime secrecy, famously helped generate electricity from nuclear energy, illuminating a single incandescent bulb. It was a stark, almost theatrical demonstration, a fragile glow against the backdrop of a shadowed past. That image, carefully curated and widely disseminated, became an enduring emblem of the atom's promised peaceful future, a beacon of hope in the post-war era. Yet, beneath the radiant promise lay the undeniable truth. This very machine had been conceived and constructed in a frantic, clandestine race for a weapon of unimaginable power. The reactor's operational journey concluded in 1963, exactly 20 years after it first achieved criticality. A full 2 decades of continuous, groundbreaking work. This extended, productive lifespan profoundly redefines X-Ten's true identity. It was never merely a wartime reactor, nor simply a historical landmark preserved for posterity. It was, in essence, a monumental bridge. A bridge spanning the vast chasm between the theoretical elegance of experimental reactor physics and the brutal industrial demands of plutonium production. It forged a path from the desperate exigencies of war to the burgeoning possibilities of peacetime nuclear science. It connected the abstract equations of theoretical chemistry with the tangible, perilous realities of remote-controlled radiochemical engineering, a field born of necessity and fraught with unseen dangers. What those brilliant minds in 1943 could not have foreseen was that Oak Ridge, in the collective memory of the future, would be primarily celebrated for its monumental achievements in uranium enrichment. The X-Ten's pivotal, almost sacred role as the proving ground for plutonium, the very heart of the atomic bomb, would slowly recede into the background, overshadowed by other narratives. This fading memory, this quiet sidelining of its true significance, is precisely why its story demands to be told now. The path to plutonium, that most elusive and deadly element, did not spring fully formed from abstract scientific theory, nor did it leap directly to the gargantuan reactors that would eventually rise in the desolate landscapes of Washington state. It first passed through the rugged hills of Oak Ridge, Tennessee, and X-10 was the indispensable machine that rendered that passage not just possible, but repeatable, scalable, and ultimately inevitable. The real lesson embedded within the story of X-10 transcends the simple fact that a reactor achieved criticality in Tennessee during the crucible of World War II. It reveals a fundamental truth about the very nature of technological progress, particularly under immense pressure. The most world-altering military technologies, the ones that shift the balance of power and redefine the course of history, almost invariably rely on a hierarchy of intermediate systems. These are not the grand, final instruments of victory. Rather, they are the silent, tireless workhorses, built not to directly win the war, but to rigorously prove that the much larger, infinitely more complex, and unimaginably expensive system can function as intended, long before everything is irrevocably committed. Chicago Pile 1, a crude stack of graphite and uranium beneath a university stadium, brilliantly proved the fundamental physics of a self-sustaining nuclear chain reaction. The sprawling industrial behemoth at Hanford would eventually handle the daunting task of plutonium production on an unprecedented industrial scale. But it was X-10, nestled in the Tennessee Valley, that forged the vital, unbreakable link between these two extremes. It transformed a breathtaking scientific possibility, a theoretical marvel, into a meticulously documented, repeatable industrial procedure. This monumental task demanded answers to timeless engineering questions, dilemmas that continue to challenge innovators to this day. How does one safely and reliably scale something inherently dangerous, moving from a laboratory curiosity to a factory-sized operation? How can an entirely new, untested system be rigorously evaluated before its full, irreversible deployment? How do engineers discern which design choices are merely temporary shortcuts, expedient in the moment, and which possess the inherent robustness and foresight to be integrated into the final, colossal machine? And how does one construct an entire, interconnected process chain, a seamless flow of operations, rather than simply assembling a collection of successful, isolated components? X-10 confronted and answered every single one of these profound questions, all while operating under the relentless, suffocating pressure of total global war. Its story, therefore, resonates far beyond the narrow confines of nuclear history. We witness this identical pattern, this indispensable hierarchy of intermediate systems woven throughout the fabric of human innovation. It is evident in the development of sophisticated radar networks, in the intricate design of code-breaking machines that turned the tide of conflict, in the monumental engineering feats of wartime bridge systems, in the evolution of resilient communication networks, and in the exhaustive, often perilous process of aircraft testing. A laboratory success, a fleeting spark of genius, merely proves that something can happen. But it is the pilot plant, the intermediate system, that proves it can happen repeatedly, reliably, under the crushing weight of real-world pressure, involving complex human teams, unforgiving schedules, and the intricate dance of logistics. It is in these unsung machines that the future is truly forged, one meticulous, hard-won step at a time. The unforgiving crucible where grand designs collide with the brutal realities of the physical world. That is the essence of a pilot project, a place where every theoretical calculation, every blueprint, every potential failure mode must be meticulously confronted and overcome. Nowhere was this truth more starkly revealed than within the clandestine confines of Oak Ridge. A once secluded valley, veiled in absolute secrecy, transformed into an unprecedented training ground. Here, a towering graphite pile ascended not merely as an experiment, but as an industrial classroom, its lessons etched in the very fabric of nascent atomic power. The X-10 Graphite Reactor, a temporary marvel of engineering, became the indispensable link, bridging the chasm between abstract scientific theory and the terrifying demands of full-scale production. It was through X-10's relentless operation that Oak Ridge, by 1943, was forged into the world's first plutonium pilot plant. A silent, unseen force, meticulously proving the impossible, one precisely engineered step at a time.